Okay guys, okay, so now that we finished that question set, I hope you guys have gotten some clear understanding of what we've done so far. Now we're going to talk about properties, right? And before that, we're going to talk about elimination reactions because they're going to come up again and again in your question paper, okay? Because elimination reactions are a chemical property of haloalkanes. So, for example, if I have a haloalkane like this, for example, 2-fluorobutane, right? And if I alcoholic AOH, we have already seen that the major product form will be this, right? Plus 2-butene plus KCl plus water, right? Dehydrohalogenation. Now, this is what we call the Zaitsev alkene, right? The more substituted alkene is called the Zaitsev alkene. I could have also got, see basically how does this reaction work? Let's just look at the mechanism real quick. So the reaction works, the mechanism is like this, okay? So there is both, again here also there is an E1 and an E2 mechanism. Elimination, unimolecular, elimination bimolecular as we discussed before, right? And the fact is, mostly this is what happens. If you have a strong base, so you need a super strong base for elimination, okay? If you have a strong base, what it's going to do is it's going to do that minus H plus which we saw, right? So it's going to take this H plus with it and run away, okay? And the carbon has no other choice but to flip this bond onto itself. But then this carbon exceeds its valency, so it has to kick this guy away, okay? That's basically how it works. There's a lot of extra specifics about this reaction. There's a lot of argument about how the plane should be. For example, these four molecules should be on the same plane. If I do it like this, right? If I do the carbons like this, in fact I have to draw the other way around. Then turns out only when the hydrogen and the chlorine are like this, right? And these four atoms are on the same plane, this can happen. So this is called an anti-periplanar conformation. All that is just way too much, but basically you need to know that the hydrogen is removed. This bond jumps here and this bond leaves, okay? There will be extremely high amounts of complications a molecule will undergo to make sure that the valency of carbon does not exceed 4, okay? You will see this time and time again that a molecule will do almost anything, okay? It will do things which you have never imagined it to do, which will defy the rules of what you learned, just to make sure that this valency of the carbon remains 4 and not more than 4 and less than 4, okay? So that is one of the most fundamental, unbreakable laws of organic chem, that valency should not change from 4. So elimination is that. So if I just give you a random compound, something like this. The thing is you have to identify first the alpha hydrogens, okay? See, I know you guys have done this in 11th grade, that's why I'm trying to go a little fast. If you are feeling a little bored, just maybe play with the 2xp or something because we'll be there this quick, okay? If you have a chlorine here, you want to look at the possible elimination products you can have. Suppose something like this. If you have this compound and you're saying alcoholic KOH, what's called a major product, right? And the answer to that question will be, you got to first look at what are the all alkenes that are possible in the first place. So, suppose I got to look at the carbon beside the carbon which has the halogen. Okay, so that will be this carbon, and this carbon, right? And you got to look at the hydrogen it has. So, what is the valency here? 1, 2, so it has 2 hydrogens, right? So, both are not very different. So, I just consider 1 hydrogen for now here. This carbon has 1, 2, 3 bonds already, right? So, it has only 1 hydrogen. This carbon also has 1, 2, 3, so it only has 1 hydrogen, okay? So, now, the possible alkenes will be those where the carbon with the hydrogen and the carbon with the chlorine form a double bond between each other, okay? So if we take this hydrogen first to be removed, this hydrogen and this chlorine will be removed to give me what? To give me this compound, okay? So we have a double bond here, this, okay? So that's one of the alkenes. Then if you assume this hydrogen is removed, right? Then there will be a double bond between this carbon and this carbon. So that will give me, right? There's a double bond here, and there's this, right? And there is this part. In bond line formula, you will not draw the hydrogens. I've just drawn the hydrogens to show you which one I'm eliminating right now. And finally, we talked about this hydrogen leaving, this hydrogen leaving. We can talk about this hydrogen leaving, right? That means a double bond here. This double bond here, how the structure looks like. and double bond here, right? So double bond. So these are the three possible alkenes. What are the other byproducts? You will get say water and KCl. So these are the byproducts which will be common for all three. So of these three, which is the most stable? You got to look at which alkene is most substituted. So this alkene has two groups here, one big group and one hydrogen, right? This alkene has 4 different groups. This alkene has 3 different groups. Okay? So of these, the most stable will obviously be this. The most substituted alkene is the most stable. Why? Because you take hyperconjugation into effect. So hyperconjugation will mean that if I look at the number of alpha hydrogens here, and here, and I add those, this will have the maximum number because it's the most substituted. Okay? So that is the argument. So this is basically the major product. This was a question asked in one of the UTs. So they will give you some big compound like this, and they will ask you to they'll say alcoholic AOH or something. So you have to find out all possible elimination products, and from that you got to choose the most stable one. Okay. Sometimes you might have some cyclic ring like this or something. Okay. All those you got to take into account. Okay. For example, if you have two big groups close together on one side, right? For example, if this was a tertiary butyl and this is tertiary butyl, they won't be stable because they're on the same side. If they're on the opposite side, it's better. All that stuff is also there. Okay. So you gotta be able to logic out, reason out like that, because that's probably where you guys get 2 sparks, because you kids are smart. So basically, the important thing you guys have to remember is find the alpha hydrogens. Wherever the chlorine is, 1 carbon away from that, you got to be able to draw double bond. Okay, that too only wherever there is a hydrogen. If there is no alpha hydrogen, no dehydrogen. Alpha hydrogen means carbon adjacent to the carbon containing chlorine or bromine or whatever. Okay, that's the first thing. Second thing is, once you've drawn out all the alkenes, the most substituted alkene, the one which has the most methyl groups on it, is the most stable alkene. Okay, this is Zaitsev's rule. So this has only 3 alkyl groups. This has also 3 alkyl groups. This has 4 alkyl groups. Okay. Other things you need to remember: if there are 2 humongous groups on the same side of alkene, maybe that's less stable. Okay, so you want to remember that. So between these two, which one do you think is more stable? I'll give you about 2-3 seconds to choose which one is more stable between these two. You'll not use that steric thing I told you about the size and stuff, right? So can you tell me which one is more stable? I'll give you about 3 seconds. Pause the video. Okay, so the answer is that this one is more stable because you have 2 small methyl groups here, and the big group has a hydrogen, so there's less steric hindrance. Here you have these 2 groups will be sterically interfering with each other, and this methyl has a hydrogen. So since there is more steric hindrance in this case, this alkene is less stable. Okay, so you could go to hyperconjugation effect and look at it, but this is generally a way of eyeballing the answer. Okay, so that is the first thing I wanted to talk to you guys about. You will see more examples where I will show you some exceptions and stuff. Okay. In fact, let me just show you one exception right now, which is if you have something like this, for example, right, a favorite example, but here you have a tertiary butyl, group. Okay. Now the point is the base. So you're going to have hydrogen here, right? Hydrogen. You also have hydrogen here. Problem is base wants to come and take away this proton, right? He generally likes to take away this proton because this bond form will remove the chlorine obviously, and this alkene will be more stable. The problem is, however, that see, this is all single bonds, okay, so they keep rotating, right? That's the point. Single bond is symmetric about in the nuclear axis, right? So it can keep rotating. The problem is if a base is going to come, right? For example, that way if I choose a very fat base, if I choose something like, I'll choose this itself. I will choose tertiary butyl. I'll do something like this. CH3, CH2, 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 O minus. Okay, so this is basically alkoxide, right? It's actually butoxide, right? And this guy has to go and come close to this H plus, right? And remove him. That's basically the point, right? You remove him and you get a butanol. But the problem is he can't come close because this guy already is fat, this guy is super fat, and they keep rotating, so he's probably going to die if he goes close by, right? So instead of having all that trouble, he says, you know what, forget about it, and he goes here and takes away this hydrogen instead, and then so this bond is formed. So at the end of the day, you will get, and this chlorine leaves obviously, so you get this compound instead. Right? So this is this is technically the less stable alkene, right? So this is what we call the Hoffman alkene. Named after Hoffman, the scientist who discovered actually a method to prepare these alkenes. Because normal methods only give you the sites of alkene, right? What if you wanted 1-butene? How do you prepare 1-butene? So Hoffman actually discovered the method of preparing 1-butene. Okay? You will need to remember all your 11th chemistry reactions, 10th chemistry and 11th chemistry reactions for 12th chemistry. If you remember any other reaction of alkyl halides, you're going to probably need them. For example, if you remember alkynes have this reaction with Ag2, right, or AgOH, or ammoniacal silver chloride solution, cuprous chloride solution. You will get C triple bond C plus, and all you get, right? Some long equations will be there. You might want to remember those. I will actually get back to you on that exact reaction. We'll do a problem based on that. Okay. Acetylide, right? The copper acetylide or silver acetylide will get. The reaction was this, right? Ethane plus ammoniacal cuprous chloride solution, for example, CuCl2, cuprous chloride. Cuprous chloride is Cuprous is CuCl, right? Cuprous chloride solution, ammoniacal, which means basically you will dissolve it in ammonium hydroxide. What does this give me? This gives me C triple bond C. So you get copper acetylide, right? So Cu plus and Cu minus. So basically you will get minus and Cu plus HCl. Right? So this is basically copper acetylide. You can do a lot of other stuff. You can jump around with this later, right? So you can convert this into a lot of other stuff, and so that's basically the point. So basically, yeah. So you want to remember your 11th and 10th organic chemistry very well. Okay. So that is another thing. All these questions will come up in your problem set. Okay, we will use things which you learned long back. Okay. Now we will quickly talk about aromatic electrophilic substitution also, because that will also come. Nitration, your reagent is what? HNO3, H2SO4, right? Sulfonation, H2SO4. So I write electrophiles here, NO2 plus, SO3. Chlorination, which is basically Cl plus, your reagent is this chlorine. Friedel-Crafts alkylation. Right? What is the reagent for Friedel-Crafts alkylation? Your methyl chloride, so Rx, plus in the presence of anhydrous FeCl3 or HCl3, right? That is another one. And finally, Friedel-Crafts acylation is also similar. See, acylation. Basically, what you might want to know is that acylation in the acylium ion and the R plus ion, right, are very weak nucleophiles. So, if you have a highly deactivated system, for example, nitrobenzene, right? Nitrobenzene, nitro group, you guys know, right, is the biggest enemy of any aromatic substance because it just sucks electrons both ways. Both inductive and resonance effect, electrons are getting sucked out, right? Which means this ring loses its electron density by a lot. Which means if you have a strong electrophile, someone who has true love for electrons, then only they'll be able to come here. If someone has superficial, like for electrons, then if the electrons just move off a little, he's not going to come. So basically, what's going on is this R plus cation electrophile and the RO plus the acylium ion and the R plus ion, right? Both of them are ones they do not believe in true love of the electron. So basically, they do not nitrobenzene cannot undergo alkylation or acylation. Okay, any deactivated system, that's the word we use. Deactivated system, basically, which means electrons are not in the ring anymore. They cannot undergo acylation or alkylation. So that's another thing you might want to know. You guys remember? I hope you guys remember ortho-chiron meta-directing groups. I think this is again a question in your problem set. In fact, we'll keep that in the problem set. I'll do some other question actually. Let us take, for example, you are in NO2 and in nitrate, what will happen? What's the product you get? Nitro is minus I, minus R and minus I, right? So it's going to remove electrons from here, here and here very much. So you get meta nitro, okay? That's one example. Let's try, in fact, let's try some other group. Let's try COOH2. Any sulfate, what do you get? So I'll give you about 2-3 seconds to guess that. Okay, I hope you got it. So basically COH, you can see that it's a minus I group, but if you just draw the structure carefully, so I'll put the C actually, C double bond O, OH, right? So you can see that these two bonds are in actually resonance. So basically what will happen is, this is minus I, and it's actually, see, basically this also has a lone pair, but these guys are generally in resonance themselves, okay? So the resonance effect of the COH actually doesn't matter. So it's broadly minus I, so you generally get meta. COH is a meta-directing group, okay? But see, COH is a little more complicated. You will learn something called ortho effect when you learn carboxylic acid and stuff. But for now, you can just take note that COH is going to be this thing, meta-directing. Okay, so remember that COH is meta-directing. Next up, in fact, let me just check my notes. I'll give you some questions from the notes I have. We can just bear with me for a second. Let us. Okay, so these were questions which Miyashima gave us. So it is given chlorobenzene. You chlorinate. She didn't give it this way, she gave it the long way. So plus chlorine and hydrous AlCl3 she gave. So what do you think is going to be the answer? Well, see, the fact is you want to know whether this is meta-directing or ortho-meta-directing, right? How do you find that out? You know that chlorine is having a lone pair. So you can always donate lone pair into the ring and start putting negative charges here. And electrophiles is a negative charge, he gets very happy. So chlorine must be ortho-para-directing, right? Which means what's going to happen? You're going to get this, and meta you get in a very low amount. Between these two, which will be more stable? Which do you think will be more stable between the ortho and the para groups? Well, inductive effect wears out by the fourth carbon, okay? You want to remember that. So, if I was here, chlorine is still electronegative, so we're still putting all the electrons back. So, this minus charge is not a super minus charge, it's a decent minus charge. But if you look at it here, this negative charge is so far away from the chlorine that the electronegativity doesn't matter. So, this guy is going to be a much more pronounced negative charge than this guy. So, this must be the negative product. And this is the second major product. And metachlorochlorobenzene is the minor product. Right? That was the first one. The second question is it's the same question except instead of chlorination you're doing nitration. So you get the same answer. You basically get NO2 instead of Cl. The third question is again the same thing except instead of nitration you do sulfonation. So you do SO3. So you get SO3H here and here instead of chlorine. The fourth one is also okay. So fourth one, let's discuss in your problem set. It's similar questions than your problem set. So I'll leave it for your problem set. Fifth one is let's do another question now. Okay, so the next question is you got chlorobenzene, right, plus RCOCl. Right, this is basically the acidium. You're doing acylation and you're doing anhydrous AlCl3 and you're asking for the major and minor products. Again, same thing. This is going to be a electrophile, right? So para is going to be strongest, ortho is going to be next strongest. So you get the same answer again. Okay, the next question you guys should have done in 11th grade. But again, remember, these are questions which you get in the exam. Okay, something like this is something you will get in the exam. Because these are simple, straightforward ones. These you might not remember. Right? So this is actually word static reaction. So dry ether, I should have mentioned dry ether. Do you guys remember why dry? If you remember why it's dry, that's good. I will leave that as homework for you. But anyways, you're going to get, this is basically a preparation of alkanes. Yes? So you might want to brush up on your 11th organic chem. But other than that, I think you guys are pretty fine, right? So maybe here's another question. Let's see. Okay, so here's the deal. If you want to prepare this compound, from benzene you want to prepare 2,4,6 trinitro-chlorobenzene, right? How will you do it? So I'll give you a few minutes to do this. Let me see if there are other questions in there. You can pause the video and then we will resume. Basically the question comes down to, okay, so I hope you guys pause it again. The question comes down to whether you introduce the nitro first or the chlorine first, right? And the answer is that you want to introduce the chlorine first, because if you introduce the nitro first, it's going to deactivate the ring and then your chlorine is not going to be able to come. Because however, see, Cl plus might be a good nitro first, okay? But due to the fact that 3 nitros are like, it's just too strong, they just suck out all the electrons completely, pretty much. So chlorine is never going to have anywhere to go. So you first introduce chlorine and then you introduce the nitros. As you can see, the nitros are in ortho-para to the chlorine, right? So there's no issue. If the nitros were meta to the chlorine, then that's a problem, okay? And that you will see in your problem set, hopefully, right? So you will see that in your problem set, but till now this is fairly enough. So this is basically winds up your electrophilic aromatic substitutions, I guess. Just keep practicing is what I can say. The test will basically have, it's basically going to judge you on how much chemistry you remember from 11th and 10th, and how much you can think on your feet, basically. That's basically it. So we talked about elimination reactions, we talked about electrophilic aromatic substitution reactions. What else do we have left? Basically, you guys have pretty much done all the reactions now. You still have some chemical properties left. For example, some weird reactions which some people do. Some of them satisfy some weird properties. For example, chlorobenzene does this thing called dose process. So you want to discuss about dose process. You can convert chlorobenzene to phenol by doing a lot of random stuff. You will see that this is phenol, by the way. It's again a common name. Hydroxybenzene is the actual name, but benzyl alcohol is this. Okay, so don't get confused. Benzyl alcohol is this. It's one carbon and then an alcohol. This is not benzyl alcohol. This is phenol. Okay, so we will see that for some reason haloarenes are very resistant towards substitution reactions. We will see that. Then we will also see some properties that we talk about boiling point trends, as I said in the previous lectures. We talk about boiling point trends, melting point trends, and all that stuff. And that will pretty much end your chapter. And then we will just discuss about your problem set. Okay, so see you guys in the next one.